Example, the Brayton cycle with intercooling. A gas turbine has two stages of compression with an intercooler between the stages. Air enters the first stage at 120 kPa, 350 Kelvin. The pressure ratio across each compressor stage is 6:1. Each stage has an isentropic efficiency of 80%. Air exits the intercooler at 380 Kelvin. The maximum cycle temperature is 1800 Kelvin and the cycle has a single turbine stage with an isentropic efficiency of 85%. Assuming the working fluid to be air throughout the cycle, calculate the temperature of the gas leaving the gas turbine in Kelvin, the mass flow rate of the air if the power output is 30 MW, the work ratio, and the cycle thermal efficiency. If we draw the Brayton cycle with intercooling, we are going to get a similar diagram like this. Next, you will have to list out all the informations given from the question. We are going to have the pressure and temperature for the state 1, the temperature at state 3, the pressure ratio is also given to us, and the isentropic efficiency for the compressor and the turbine. Note that process 1 to 2 and 3 to 4 will consume work. For the intercooling process, portion of heat will be removed. For process 4 to 5, it will be constant pressure heat addition to our system. For process 5 to 6, we are going to produce the work out by the turbine. And process 6 to 1 is the constant pressure heat rejection. Now let's have a look at the items requested by this question. The temperature of the gas leaving the gas turbine in Kelvin will be the temperature at state 6. The next item will be the mass flow rate of the air if the power output given is 30 MW. We can find the mass flow rate by using the equation of power output is equal to mass flow rate times with Cp times with T5 minus T6. For the work ratio, we can determine by using the back work ratio formula, which is power input divided with power output. And lastly, for the cycle thermal efficiency, we can determine by using the formula of power net out divided with heat transfer rate in. If we look at the list of equations to determine the required items requested by the question, we need to find the temperature at state 1, state 2, state 3, state 4, state 5, and state 6. Note that if it is given to us the isentropic efficiency for the compressor and turbine, we can now find the actual properties leaving our devices. In our case, that will be state 2A, state 4A, and state 6A. Later, we are going to use these actual values in our analysis. Now we are going to find the temperature for each states. For state 1, the temperature is already being given from the question. T1 is equal to 350 Kelvin. For state 2, first we are going to find the temperature at state 2S by using the isentropic relation between the temperature and pressure. Note that P2 over P1 is equal to the pressure ratio Rp. Once we obtain the value for the ideal temperature at state 2, next we are going to find the actual temperature at state 2 by using the isentropic efficiency given to us for the compressor is 0.8. Now we can have the values for the actual temperature at state 2. The temperature at state 3 also has been given from the question, which is 380 Kelvin. In order for us to find the actual temperature at state 4, first we are going to find the value of T4S by using the isentropic relation between temperature and pressure. And note that P4 over P3 is equal to the pressure ratio Rp. Once we substitute the values and calculate, we are going to get the value of T4S is equal to 634.03 Kelvin. By using the isentropic efficiency for the compressor, which is 0.8, we can now find the value for the actual temperature at state 4. We are going to get T4A is equal to 697.54 Kelvin. The temperature at state 5 is also has been given by the question, which is 1800 Kelvin. For state 6, first we are going to find T6S by using the isentropic relation between the temperature and pressure. Since P1 is equal to P6, P2 is equal to P3, and P4 is equal to P5, we can have the relation of P5 over P6 is equal to P2 over P1 times P4 over P3. Thus, the value of P5 over P6 is equal to 36. Once we substitute all the required values and calculate, we are going to get the value of T6S is equal to 646.67 Kelvin. By using the isentropic efficiency for the turbine, we can now find the values for the actual temperature at state 6. We are going to obtain the value of T6A is equal to 819.67 Kelvin. Once we have all the required temperatures, we can now solve the items requested by the question.